Hello friends, in this video we are going to see about thermodynamics and the four laws of thermodynamics. Some brief concepts in thermodynamics will be discussed, and then we will see about the four laws which are present in thermodynamics. So, introduction. So what is a thermodynamic system? A thermodynamic system is a body of matter or radiation confined in space by walls with defined permeabilities and separated from its surroundings. The surroundings may include other thermodynamic systems or physical systems that are not thermodynamic systems. So a wall can exist in theory, but only in theory. So it is not a wall. A thermodynamic system is going to be something which is going to be within a container where insulation is going to take place to prevent the heat energy and like whatever necessity precautions needs to be taken, the process will be taken care of. Next, there are microstates and macrostates in thermodynamics. So macro and micro in general will refer to as a big thing and a small thing. So there is here in thermodynamics it denotes the two ways of looking at a system. So macro state will involve a huge amount of transfer of matter, large enough for us to measure its volume and pressure or temperature or density, that is whichever is going to be in bulk. A microstate isn't just about a small amount of matter, it is detailed look at the energy that molecules or other particles have. So for example, if you flip a coin twice, we will get different things like heads, all the probabilities we will note down: head tail, tail head, tail, and so on. And so if you see, head tail and tail head are going to be the microstates, and whereas when we say that head tail and tail head, we have got the combination, like a head tail combination is going to come 2 out of 6 states, something in that sort. Then we are going to say it's macro state. This is how we can understand the micro and macro states in thermodynamics. And next we see statistical thermodynamics. The primary goal of statistical thermodynamics, also known as equilibrium statistical mechanics, is to derive the classical thermodynamics of materials in terms of the properties of their constituent particles and the interaction between them. In other words, statistical thermodynamics provides a connection between the macroscopic properties of materials in thermodynamic equilibrium and the microscopic behaviors and motions occurring inside the material. So whereas statistical mechanics, it involves the dynamics, here the attention is focused on statistical equilibrium. So statistical equilibrium. So usually, like nowadays, what they are saying is like statistical equilibrium, statistical thermodynamics can also be called as probability thermodynamics. It has more to do with probability, so it can also be called as probability thermodynamics. But it is the most commonly used term is statistical thermodynamics and statistical mechanics. So statistical equilibrium does not mean that the particles have stopped moving. That is mechanical equilibrium. The particles are still moving, but the only thing is the ensemble, the group is not evolving. We will see the definition of ensemble soon. Like after seeing statistical mechanics, the next slide will be about ensemble. So statistical mechanics is a branch of statistical physics that deals with the description of physical phenomena in terms of the stochastic, having a random probability distribution that may be analyzed statistically but may not be predicted precisely. Behavior of large numbers of components such as atoms or molecules, especially regarding the distribution of energy among them. So statistical mechanics is a branch of statistical physics. So this is one part. It deals with the description of physical phenomena in terms of the stochastic behavior of large number of components. So what is stochastic? Stochastic is which is having a random probability distribution that may be analyzed statistically but may not be predicted precisely. So it involves the discussion of stochastic behavior of large number of components such as atoms or molecules, especially regarding the distribution of energy among them. Statistical mechanics provides exact methods to connect thermodynamic quantities such as pressure, temperature, heat capacity to microscopic behavior. So microscopic behavior involve parameters that fluctuate about average values. For example, if we take one state, small state E1, and if we will take that E1 state to be the main state and the surrounding states, nearby states to be equal to 0, something like that. So the fluctuate, there will be, even though there is going to be standard variation or thing, we will be ignoring those things. And so E1 state is going to have this value, on an average it is going to have this value, E2 is going to have on an average this value. So we are going to take in that way. So and these are characterized by probability distributions, and this microscopic behavior and the statistical mechanics, all these things came out of classical thermodynamics. It is not that from statistical mechanics classical thermodynamics came out. It is from classical thermodynamics that statistical mechanics arose because of the curiosity and the interest of some scientists who are concerned with microscopic behavior which could impact on a macroscopic level. They designed this statistical mechanics field. So just the previous slide, this is statistical thermodynamics. We can see that statistical thermodynamics is differing from statistical mechanics in a way that statistical thermodynamics is to derive classical thermodynamics of materials in terms of the properties of their constituent particles and interactions between them. Is to derive the classical thermodynamics of materials. In other words, statistical thermodynamics provides a connection between the macroscopic properties of materials in thermodynamic equilibrium and the microscopic behaviors and motions occurring inside the material. So macroscopic properties which are in thermal equilibrium with the microscopic properties. So if there is no mechanics is going to involve dynamics, then statistical thermodynamics is going to involve equilibrium. And next, if we go, we are seeing methods to measure microstates. So for example, some people will say it is micro, so how can we measure? If some people have the doubt, so these are some of the techniques that are used to measure microstates. So spectroscopy, scattering techniques, molecular dynamic simulations, electron microscopy, quantum chemistry, mass spectrometry, calorimetry, fluorescence and absorption spectrometry, surface science techniques, Fourier transfer, infrared spectroscopy. These techniques are used to measure the microstates at various time intervals, and then based on that an inference is drawn, and based on that the macro level it is all the averages are summed up and we get the macrostate. So matter, next we are seeing the definitions of matter, energy and ensemble. Matter is any substance that has mass and thereby volume and space. So if a gas is made to have volume when it is compressed, it is a matter. So energy is ability to do work. Thermal energy, radiant energy, chemical energy, nuclear energy, electrical energy, motion energy, sound energy, elastic energy, gravitational energy. All these are various sorts of energy. Mostly in thermodynamic systems, we'll mainly concern ourselves with thermal energy. And in an ensemble is a collection of possible states of a system, each with an associated probability. So ensemble is a group. 2 slides back, if you can recall, I mentioned ensemble as a group. Here the exact definition is, it is a collection of possible states of a system. The collection of possible states of a system, each with an associated probability. So for example, a particle can exist in for example say 3,2 in a Cartesian coordinate system, and the same particle at a different time interval it can exist in 2,3 in another state. So these two can be considered as two different states, and the ensemble approach allows so collection of all these states is what is known as ensemble. The ensemble approach allows for the consideration of range of possible configurations rather than focusing on a single state. So this helps us in consideration of range of possible configurations, how it can work in this configuration, how it can work in that configuration, how it can work. So all these things will be taken into consideration, and based on that the values and the parameters, the input output things can be devised so that we will get the best possible results. That's why this ensemble approach is done. And next, if we see types of thermodynamic ensembles, so there is a microcanonical ensemble, then there is canonical ensemble, then there are other things called as grand canonical, isoenthalpic, isobaric, isothermal, isobaric ensembles. So microcanonical ensemble is a statistical ensemble. All these are statistical ensembles. So statistical ensemble where system is assumed to be isolated. As we saw, the systems are usually thermodynamic systems are going to be having three states. These are the three states: isolated, closed, and open. So isolated thermodynamic system has no energy transfer nor matter transfer. Closed thermodynamic system has energy transfer but no matter transfer. Open thermodynamic system has both energy transfer and matter transfer. So isolated thermodynamic system means there is no contact with the world, something like no contact with the world. So closed means it has energy transfer alone, and open means it has both energy and matter transfer. And like in when we consider in case of ensembles, statistical ensemble where system is assumed to be isolated. The thermodynamic system is going to be assumed to be isolated. So number of particles n, v, number of particles n and volume v and energy E are assumed to be constant. So this ensemble is called as NVE ensemble. And canonical ensemble is a statistical ensemble where system is assumed to be closed, that is only energy transfer, no matter transfer, but here it is assumed that it is in thermal equilibrium with a heat reservoir. Heat reservoir can also be said as a heat bath at a fixed temperature. So this ensemble depends on number of particles n, volume and temperature. There first case microcanonical, it is energy. Here in the second case it is canonical, it is the case of temperature. So this ensemble is called as a NVT ensemble, and there is also called as a grand canonical micro VT and isoenthalpic isobaric NPH, isothermal isobaric NPT ensembles. Each ensemble will play an important role in one type of thermodynamic system. So for example, I am stating it might not be the exact case, like in case of protein folding mechanism, when we study where the equilibrium will be there, we will consider the NVT ensemble. So next, if you see Boltzmann's equations. So Boltzmann equation in statistical mechanics, Boltzmann equation also known as Boltzmann-Planck constant. Why we are studying about Boltzmann equation means Boltzmann equation comes in to play in thermodynamics. So just for that, before we go into the laws of thermodynamics, we will see about the Boltzmann equation. So statistical mechanics, Boltzmann equation also known as Boltzmann-Planck equation is a probability equation relating to the entropy, also written as SB of an ideal gas, to the multiplicity denoted as omega or W, the number of real microstates corresponding to the gas macrostate. So S is equal to Kb into ln V. Kb is the Boltzmann constant. And it is 1.380649 into 10 power minus 23 joule per Kelvin, and ln is the natural logarithmic function. So in short, the Boltzmann formula shows the relationship between entropy and the number of ways the atoms or molecules of a certain kind of thermodynamic system can be arranged. So next we will go, this is in microscopic, it is also like kind of a microscopic and a macroscopic connection. So this plays a role in the thermodynamics. We will see how the laws of thermodynamics has different parameters, and in those parameters how the microstates and the macrostates play a role. So this is just an introduction. This is not in detail. So this is all basic concepts. Another detailed video will be covered very soon. Next, types of thermodynamic system was discussed previously. Next, the laws of thermodynamics. So zeroth law of thermodynamics. So this is like a theory of associativity. Like in case of algebra, if associative property of numbers is there, so A equals C, B equals C, therefore A equals B. So this is like that. So what the zeroth law of thermodynamics states is, if two systems are both in thermal equilibrium with the third system, then they are in thermal equilibrium with each other. So this is simple law. It is a foundation of temperature as an empirical parameter in thermodynamic systems. So the empirical parameter means a parameter which can be observed. So in thermodynamic system, how temperature plays a role. So that role is being mentioned in the zeroth law of thermodynamics. Next, first law of thermodynamics. So in first law of thermodynamics, total energy of an isolated system, that is a system that has no energy and matter transfer, is constant. It is a version of law of conservation of energy. Energy can neither be created nor be destroyed, but it can be transformed from one form to another. So if we take in classical mechanics, Newtonian mechanics, we know that total energy is equal to potential energy plus kinetic energy. So potential energy is the energy stored in the system, that is inherent, the potential, the capacity to do work based on the constituents. Whereas kinetic energy is the energy based on the movement or motion. So the first law of thermodynamics for an isolated system is like the inherent potential energy. It is stored in for an isolated system. It is the inherent potential energy which is stored in the system. It has the capacity, this much capacity to do the work, and it is not going to get destroyed. Because there is no kinetic, and then there will be no kinetic energy. And for a closed system where there is energy transfer but no matter transfer, there is an internal change of energy. So closed system means there is an energy transfer and there is no matter transfer. So the energy transfer can be taken as a thermal energy transfer. So in this case, there will be an internal change of energy which is equal to the energy supplied or withdrawn, usually amount of heat minus the work done by the system. So if you are going to, for example, if you are going to supply heat and based on the heat, the piston moves up. For example, the piston in the system moves up based on the heat. So how much amount of heat is applied and the work done by the system minus the work done by the system, it's going to be the internal energy of the system. Next, if you see the second law of thermodynamics, there are two different statements for the second law of thermodynamics. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a cooler to a hotter reservoir. So like we have to deconstruct the sentence in order to understand for the first timers. So how we have to deconstruct this sentence is like, it is impossible to construct a device. So what kind of device that operates in a cycle and also produces no effect other than the transfer of heat from a cooler to a hotter reservoir. So in simpler terms, the second Clausius statement is, it is impossible to construct a device that operating in a cycle produces no effect other than the transfer of heat from a cooler to a hotter body. So it is second law of thermodynamics indicates the irreversibility of natural processes. And in many cases the tendency of natural processes to lead towards spatial homogeneity, and the quality of being the same for all, of matter and energy, especially of temperature. Entropy and second law. Clausius statement emphasizes that heat cannot spontaneously flow from a colder object to a hotter object without external work being done on the system. So from a colder object to a hotter object, if heat is going to flow, then some external work has to be done on the system. Based on the work only, the heat is going to get transferred. The heat is going to transfer, like the work, based on the work is going to get converted into heat energy or something, and then it is going to go to the hotter object. From there it is going to go to the hotter object. So entropy is a thermodynamic property that measures the degree of disorder or randomness in a system. So entropy is a thermodynamic property that measures the degree of disorder or randomness. How can disorder or randomness be measured? So for that, we are going to see about, like in statistical mechanics, it is related to the number of microscopic arrangements or configurations that correspond to a macroscopic state. So as we saw previously, like there is going to be, for example, a state is going to be there like dice is going to be there. Dice is going to have like when we throw a dice or a coin, we are going to get a head and a tail. So head h comma t is one combination, and t comma h is one combination. These two are like micro. And then, but whereas when we say in combination, like a permutation, these two are permutation, and combination when we say head and a tail. So it is related to the number of microscopic arrangements or configurations. So ht and th are going to be two microscopic arrangements or configurations that correspond to a microscopic state, head and a tail. So this is how this entropy is related. In any energy transfer or transformation, if no energy enters or leaves the system, the potential energy of the state will always be less than that of the initial state. In energy transfer or transformation, if no energy enters or leaves the system, that is, it is going to be either isolated system, it is going to be mostly an isolated system, the potential energy of the state will always be less than that of the initial state. That is, entropy in an isolated system never decreases. Why in isolated system there need not be energy transfer, but if there is going to be energy transfer or transformation, then without any it is like Newton's second law. A body will tend to be act on a motion straight line unless and until acted by the opposite force. It is inertia concept, something like that. If no energy enters or leaves the system, the potential energy of the state will always be less than that of the initial state. That is, entropy of an isolated system never decreases. It will just continue. The body is going to continue in the same motion. Next, if you see work and heat. So work, what is the concept of work and heat? So small or infinitesimal change in work is equal to the pressure times pressure multiplied by the volume change. That is going to be the work. This will be applicable in case of isothermal process mostly. Like that temperature is going to be is going to supplied, then the piston is going to move up when the constant temperature is applied. So piston is going to move up and the pressure is going to be constant. So in situations like this work is done based on the change in volume. So based on change in volume, and similarly there is an infinitesimal change in heat, means that is equal to the constant temperature in the system multiplied by the change in entropy. So change in delta Q is equal to T into ds. And overall, if we see, change in internal energy of the system, that is equal to change in internal energy of the system is equal to here for a closed system where there is energy transfer but no matter transfer. So du is equal to Q minus W. So du is equal to Q minus W. So Q is going to be TdS and W is going to be PdV. So du is equal to TdS minus PdV. So this is one equation. The U is nothing but the internal energy of the system. So if you see, everything is getting covered. The internal energy concepts and the pressure, temperature, every macro, that is every observable property that is in macro state is linked with other properties. We will see more in detail in next to few slides. So next is third law of thermodynamics. In third law of thermodynamics states that the entropy of a closed system at thermodynamic equilibrium approaches a constant value when its temperature approaches absolute zero. So third law of thermodynamics, entropy of a closed system. Closed system is nothing but where there is energy transfer. So at thermodynamic equilibrium approaches a constant value when its temperature approaches absolute zero, minus 273 degrees Celsius or 0 Kelvin. So this constant value cannot depend on any other parameters characterizing the system, such as pressure or applied magnetic field. At absolute zero, the system must be in a state with the minimal possible energy. So the Nernst statement of the third law of thermodynamics concerns the thermodynamic process at a fixed low temperature. The entropy change associated with any condensed system undergoing a reversible isothermal process approaches zero as the temperature at which it is performed approaches zero. So overall, the entropy cannot, it's difficult to make the randomness or disorder of the system to zero. There will be some disorder, and only when absolute zero is going to be reached, then the thermodynamic equilibrium approaches a constant value. The entropy of the closed system at thermodynamic equilibrium is going to approach a constant value. Otherwise, the entropy is not going to remain constant. So this is the micro and macro connections. All the three laws of thermodynamics are linked with some microparameters. So these microparameters, as we have seen, can be measured through various methods. So for example, the internal energy of the macro state is the mean over all micro states of the system's energy. So this is a microscopic statement of the notion of energy associated with first law of thermodynamics. For more general case of the canonical ensemble, the absolute entropy depends exclusively on the probabilities of the microstates and is defined by minus kb s is equal to minus kb into summation of I is equal to 1 to omega pi into ln pi, where kb is the Boltzmann constant for the microcanonical ensemble consisting of only those microstates with energy equal to the energy of the macrostates. This implies S is equal to kb into ln omega, where omega is equal to number of microstates, that is equal to 1 by pi. Pi is going to be the probability of the each individual state, P1, P2, P3, etc. So EA, first case is EI, and the second case is E1, E2, E3. So for corresponding probability, this above, after internal energy is over, this is first law of thermodynamics. And second, the next thing is for when it is entropy is coming, then it is the second law of thermodynamics. And similarly, heat and work can be distinguished if we take the underlying quantum nature of the system into account. So for a closed system, no transfer of matter. Heat in statistical mechanics is the energy transfer associated with disorder microscopic action on the system associated with jumps in occupation numbers of the quantum energy levels of the system without change in values of the energy levels themselves. So how heat and work can be distinguished? Work is the energy transfer associated with an ordered macroscopic action on the system. If this action acts very slowly, then the adiabatic theorem of quantum mechanics implies that this will not cause jumps between energy levels of the system. In this case, the internal energy of the system only changes due to a change of the system's energy levels. The microscopic quantum definitions of heat and work are the following. So delta W is equal to summation over I is equal to 1 to n pi into change in EI. Delta Q is equal to summation over I is equal to 1 to n EI into change in probability. So that d is equal to delta W plus delta Q. The above two definitions, this definition was discussed previously. D is equal to delta W plus delta Q. So this is how the two above definitions of heat are among the few expressions of statistical mechanics where the thermodynamic quantities defined in the quantum case find no analogous definition in the classical limit. The reason is that classical microstates are not defined in relation to a precise associated quantum microstate. Which means that when work changes, the total energy available for distribution among the classical microstates of the system, the energy levels, so as to speak, of the microstate do not follow this change. So when there is going to be something macro change also is going to be there, the micro level states are not going to follow some corresponding change. So there is, because of this disorder, there will be different values and different expected results may not match. Expected results might not match. So because of that, we are studying this connection between the microstates and the macrostates in order to get the best possible results from a thermodynamic system. So I think this is the end of the video. There is definitely more to this than that meets the eye. So because it's a thermodynamics field, and what I have covered is just very normal thing, I know definitely, and this is the basics, and I will come up with better explanations, illustrations, and better talk possibly. There might be many mistakes which I might have made, and I apologize sincerely for those mistakes. Thanks a lot for watching. Thank you.